Hello and welcome to this GCSE Chemistry video about the three states of matter. In this video we'll obviously cover what those three states of matter are and how we can represent them using state symbols. We'll move from there into changes of state and melting point and boiling point, and then we'll focus in on the particle model, what that tells us about the arrangement and the movement of particles, and we'll link that back into what happens during a change of state. The three states of matter are solid, liquid and gas, and we can use state symbols to represent those terms. We use an S for solid, an L for liquid and a G for gas. And it's possible to change a substance from being a solid into a liquid, and we call this process melting, but we could also turn a liquid back into a solid, and this is called freezing. A liquid can turn into a gas, and this is called boiling, and a gas can turn back into a liquid, and this is called condensing. The processes of melting and freezing actually both take place at the same temperature, and we refer to this temperature as the melting point. And the boiling and condensing processes also both take place at the same temperature, and we call this temperature the boiling point. Pure substances, whether they are elements or compounds, will melt and boil at specific temperatures. For instance, water. Pure water has a melting point of 0 degrees C, and so that means that if you have a cube of ice, it will melt at exactly 0 degrees C. And water has a boiling point of 100 degrees C, so pure water will always boil at exactly 100 degrees C. This means that at temperatures below 0 degrees C, there isn't enough energy to turn the solid water, the ice, into liquid water, and so water will be a solid at temperatures below 0 degrees C. Once we've reached temperatures above 0 degrees C, there is enough energy to melt the water and turn it into liquid, but it's not yet turned into a gas. But then when we reach a temperature of 100 degrees C, that liquid water can begin boiling and gradually turn into a gas. And so at temperatures hotter than 100 degrees C, water will exist as a gas. You need to be able to predict the state of matter substances will exist in at different temperatures, and these might be substances that you know or ones that you've never even heard of. For instance, bromine with a melting point of -7 degrees C and a boiling point of 59 degrees C. Well, if we show a thermometer again with the melting point and the boiling point marked on the left-hand side, we know that below that melting point, bromine will be a solid. Above that melting point, it will be a liquid until we get above the boiling point, and then that will be a gas. And so at 30 degrees C, for instance, 30 degrees C is up to here, which is above the melting point of bromine. So at this temperature, bromine will have converted from a solid into a liquid, but it is below the boiling point, and so bromine will be a liquid rather than a gas. At a temperature of 70 degrees C, though, this temperature is greater than the melting point and also the boiling point of bromine, and so bromine will have turned from a liquid into a gas at this temperature. For my second example of potassium, I'm not going to show a thermometer, as you probably wouldn't have time to draw one of those in a test, so I'm just going to focus in on the melting point value, which is 63 degrees C, and the boiling point value, which is 760 degrees C. And so what will the state of matter be for potassium at 30 degrees C? Well, the question we need to ask ourselves is this hot enough to melt potassium? Well, no, it's not hot enough because the melting point is 63 degrees C, which means that potassium won't melt until we exceed that temperature. And so that means that potassium will be a solid. It isn't hot enough to melt at that temperature. What if you've been asked about a different temperature at 70 degrees C? Is this temperature hot enough to melt potassium? Yes, it is. But it's not hot enough to boil potassium because potassium would not boil until we reach 760 degrees C. And so that means that potassium will be a liquid at this temperature because it is hot enough to melt the potassium but not to boil it. Sometimes, when we write symbol equations, we also include something called state symbols. State symbols tell us the types of substance that are involved in a chemical reaction. And the state symbol notation is representing one of the states of matter. And the three most common states of matter are solid, or liquid, or gas, and they are given the symbol little s, little l, or little g, and they are enclosed inside brackets. There is another state of matter that often appears in chemical equations, and that is aqueous. And that is a substance that has been dissolved in water to make a solution. And sometimes this is actually referred to as an aqueous solution. And that's given the state symbol little a, little q for the first two letters of the word aqueous. And that's also included in brackets. The purpose of state symbols is to give us some extra information about the chemicals involved in the reaction in a way that doesn't take up much space, it's quite quick, and we're just writing one extra letter in the brackets, and that tells us about the reactants or the products. It also gives us some kind of clues about what we might expect to observe during the chemical reaction itself. For instance, is a gas produced? And this would tell us whether or not we could expect to see some kind of bubbling during the reaction. Looking at some examples of symbol equations that have got the state symbols included, you can see they do tell us quite a bit about the chemicals involved. For instance, the magnesium that is reacting with the sulfuric acid, the magnesium is a solid, and the sulfuric acid is dissolved in water to make a solution. That tells us quite a bit about the reactants in this chemical reaction. And the product that they are forming has got magnesium sulfate dissolved in water and hydrogen as a gas. And so in this chemical reaction, we would expect to see bubbles of gas forming, and they would be hydrogen, and we could test for that with a lit splint and we'd expect to hear a squeaky pop. We'd also start with a solid, and over time, that solid would no longer be visible, so we would expect that to be another observation as well. In this second example, calcium carbonate is a solid, and sulfuric acid is a solution. At the end of the reaction, you'll notice that we don't have any solids, so we'd observe that solid disappearing or getting smaller and smaller. But we'd also observe bubbling again because carbon dioxide gas is produced this time. In the final example, we're starting with two things that are both dissolved in water, two aqueous solutions. But at the end of the reaction, our products, one of them is a solution, but the other one is a solid. And so in this reaction, we'd expect to see the formation of a solid, which we'd call a precipitate. So this reaction would produce a solid that was insoluble. A scientific model is a simplified representation of an idea, and this idea can help scientists to understand, to predict, or to test real-world objects or systems. In the particle model, the particles are represented by small, solid spheres, and we draw them as two-dimensional circles. And all of the particles in one particular substance should be drawn as the same size, so it's important to draw them carefully. But particles of different substances would be shown as different sizes and possibly as different colours. In a solid, the particles are in fixed positions, and they aren't moving around, the particles are vibrating about that fixed position. They're moving from side to side a tiny bit, and we call those movements vibrations. And they are in a very regular, ordered arrangement, and they are usually entirely symmetrical, but there certainly is a repeating pattern. And solids have got a definite shape and a volume. In other words, their shape and their volume can't change. Liquids are probably the hardest particle diagram to draw, and so you probably won't be asked to do that in a test, but you might be asked to describe it. In a liquid, the particles are randomly arranged, but they are still very close together. And they're free to move rather than vibrate. So they are moving around and moving past each other in this particle model for a liquid. Liquids have got a definite volume. That means the amount of space that they occupy can't change, but liquids can flow because their particles can move. And that means that liquids will fill up a container from the bottom upwards until that volume has been spent. The particle model for gases will involve drawing the fewest particles of all because gases are very far apart in terms of their particles. And in fact, most of a substance that is comprised of a gas is in fact empty space. And so you can tell that from the particle diagram that I've got here. There is no symmetry to the arrangement of my particles. It looks entirely random, but actually I'm not drawing many particles because I'm showing mostly empty space. The particles in a gas are free to move around, and they move quickly and they move at random, but they do move in straight lines, so their collisions lead to random appearing motion, but the particles will continue in straight lines until they have a collision. A gas will fill any container that you put it into, and so that means that gases do not have a definite shape or a definite volume. They are not fixed at all. We know that atoms are the building blocks of matter. They are the smallest unit that makes up everything around us. When lots of atoms come together, they form materials with specific properties that are known as bulk properties. For instance, the hardness of a material or its thermal and electrical conductivity. One metal atom, one atom of copper, for instance, cannot conduct electricity. Conductivity is a bulk property, which means it only arises because of the interactions and the arrangements of many atoms or molecules or ions joined together. So this property is the same whether you have 1,000,000 atoms or 1 billion billion. Melting point and boiling point are examples of bulk properties. For instance, a sample of solid potassium will not melt until it reaches its melting point of 63 degrees C, whereupon the particles in that sample will spread out and become a little bit more disordered. However, one atom of any substance cannot be considered to have a melting point because it is already separated out from other atoms. So while individual atoms are undoubtedly crucial, it's their collective behaviour that gives materials their bulk properties. Models simplify an aspect of our world in a way that makes it easy to understand and easy to work with. But because they are simplifications, they don't always represent a situation fully. And so as a result of this, there are some limitations as to how accurately the particle model represents particles and their interactions. For instance, there are no forces shown on particle diagrams, and we know that there are forces between the particles and that these can vary from very strong in some substances to almost zero. Additionally, in particle diagrams, all particles are shown as spheres. And whilst it's acceptable to refer to atoms as being spherical in shape, molecules definitely are not. Their shape can vary. In the particle model, the spheres are represented as being solid and inelastic. However, we know that most of an atom is empty space, and in fact, in a molecule, the atoms aren't actually directly touching at all. And finally, the sizes of the particles and the gaps between atoms are not shown to scale. We know that atoms can vary in size and that molecules can contain a range of different numbers of atoms, from 2 in a diatomic molecule like oxygen to 60 in C60 Buckminster fullerene, or even thousands and millions in a polymer. And so this is definitely another big limitation of the particle model. Particle theory can be used to help explain changes of state. The particles in a solid are held together in ordered rows and a regular pattern. and the particles are not free to move around, only to vibrate about a fixed position. And this is because there are strong forces between the particles holding them in that fixed position. In order to turn a substance from a solid into a liquid, these forces need to be overcome or at least weakened. And so energy needs to be put in for this to happen. And this energy is only supplied once a substance reaches its melting point. Once a substance has been turned from a solid into a liquid, there are still forces between those particles, but they are weaker than previously, which is why the particle arrangement for a liquid is much more disordered and more random than it is for a solid. Breaking these forces is necessary to convert a liquid into a gas, because once a liquid has turned into a gas, those particles have actually got no forces between them. And that's why the gas particles are arranged entirely randomly and entirely separately, and they're very disorganized. And the energy required to convert a liquid into a gas is supplied once a material reaches its boiling point. The amount of energy needed to change state from solid to liquid and liquid to gas will depend on the strength of the forces between the particles. And the type of substance itself, so that means its structure or its bonding, will affect the type of particle a substance is made up of. And so this could mean we're talking about molecules, or we could be talking about ions in a lattice. And this will affect the type of force between the particles of that substance and the strength of these forces. A useful generalization to keep in mind is that the stronger the forces between particles, the harder they will be to separate. And so the higher the melting and boiling points will be for that substance. We can use the particle model to explain what might happen if we did an experiment to heat up a material with a continuous supply of energy and measured its temperature over time. When the solid sample is heated, the particles will gain energy, and so they will vibrate more, and their temperature will increase. This increased vibrations about their fixed position is why a solid sample will expand slightly when it's heated. As the particles in the solid vibrate more and more, the forces between these particles weakens. Once we reach the melting point of this substance, the particles have enough energy to break free from their fixed positions, and the solid will turn into a liquid. During this process, the temperature will not increase, even though energy is still being supplied. And that means that the energy is not going into making this substance hotter. The energy is being used to break the forces between the particles and turn this solid into a liquid. As this liquid is heated, it gains more energy, and so its temperature will increase, and the particles in the liquid will start to move faster, and they will actually spread out slightly, and that's why a liquid substance will also expand slightly when it is heated. Once the liquid reaches a specific temperature, its boiling point, the particles have enough energy to overcome the forces between them, and the particles will spread out further, and they will become a gas. During this process, the temperature of the liquid will not increase, and this will be because the energy is not going into raising the temperature of this substance, it's going into overcoming the forces between the particles of the liquid. And finally, if we continue to heat this sample of gas, its temperature would of course continue to increase. If we started with a gas that had been heated to a high temperature and then allowed this gas to cool down, measuring its temperature as it did so, we would see the temperature drop over time. And this is because the particles have got less energy. And when the particles have got less energy, they will move around less and their temperature will decrease. And then once we reach the boiling point of this gas, the particles have lost energy, and so now they don't have enough energy to overcome the attractive forces between the particles, and so the forces between the particles are strong enough to pull them together, and this means that the gas becomes a liquid and a change of state occurs. This liquid will continue to cool down, lose more energy, and the particles will become less free to move. And eventually, the forces between the particles will pull them together even further, and the liquid will turn into a solid. And this will happen at this substance's melting point, and during this process of changing state, no temperature change will occur because of these forces forming between the particles. And now the particles will be held together firmly in a fixed position, and so that they can only vibrate, and the substance has become a solid. And then this solid would continue to cool until it reached room temperature. Okay, that's the end of this video. Thanks for watching.